Welcome to iLecture Online, and here's a good example to help us understand rotational motion. So let's read the problem. It says an airplane propeller, 1.2 meters in length, is rotating at 2,000 RPMs. What is the angular velocity? How long does it take for the propeller to turn through an angle of 150 degrees? What is the tangential speed of the tip of the propeller, and what linear distance does the tip cover in 1 second? So to help us along, I wrote down the linear equations of kinematics and the equivalent rotational equation of kinematics, and we'll probably need a few more equations to relate, for example, the angular distance to linear distance along the edge of the circular motion. So we'll get to that in just a moment. But first of all, imagine that we have a propeller, and I'll just draw one propeller right here, which is rotating at a certain speed, rotational speed. The length of the propeller, L, is equal to 1.20 meters, sometimes also thought of as the radius of motion. So we'll put an R there. And it's rotating at 2,000 RPM. So rotational motion is described by angular distance, angular velocity, and angular acceleration alpha. So in this case, I believe we're talking about rotational velocity. So we'll write omega, and it's equal to 2,000, and RPMs means revolutions per minute, so that is revolutions per 1 minute. And of course, the standard units for omega, for angular velocity, is a radians per second. So we'll have to convert from revolutions to radians and from minutes to seconds. So we need two conversion factors. Like so. Since we want to get rid of revolutions and replace it by radians, we'll put radians at the top, revolutions at the bottom. And of course, in one revolution, one circle, there are 2 pi radians. So one revolution, 2 pi radians. So that gets rid of the revolutions. And now we have to go from minutes to seconds. So 1 second at the bottom, minutes at the top, and of course 1 minute is 60 seconds. So now the minutes disappear, and notice that now we have radians per second, which are the standard units for angular velocity. So let's grab our calculator, figure out what that is. So we have 2,000 times 2 times pi, and divided by 60. And that means we have 209, rounded off to the nearest radian, 209 radians per second. Now, radians, being the standard unit for angular velocity, is one of those units you don't really need to mention. You can actually say that this is equal to 209 per second. You don't have to write radians, but for clarity, I usually do. So either answer is correct. Okay, going on to part B. So this is for part A. Part B, they now want us to find out how long it takes for the propeller to turn through an angle of 150 degrees. So let's say it starts at that location right here, and it travels through an angle of 150 degrees, so theta equals 150 degrees, and we want to know the time. How long does it take? Time equals question mark when theta equals 150 degrees. That's for part B. And so for that, we're going to do the equivalence of the distance and rate equation. For example, distance is equal to velocity times time, and the rotational equivalent to that would be theta is equal to omega times time. And so if we then go ahead and solve this equation for t, we have t is therefore equal to theta divided by omega. And then of course, if we know the distance and we know the omega, we can find out the time. So for part B, we can say that the time is equal to theta over omega. Now, the numbers they gave us, this was 150 degrees, so 150 degrees, and the omega that we found was 209 radians per second. Now, we cannot yet divide 209 into 150 because we have to convert from degrees to radians. Remember, standard units for rotational motion is radians, so we have to have a conversion factor here. We want to go from radians to degrees, so degrees and radians. And so there's 180 degrees in pi radians, or 360 degrees in 2 pi radians. All right, so now we can get rid of degrees, and now we have radians over radians per second, so the radians cancel out, and the 1 over seconds in the denominator will turn into seconds. So now we can calculate what that is equal to. So we have 150 divided by that, so let's say the inverse of my answer, times 150 times pi divided by 180. And there we go. So this is equal to 0.0125 seconds. So that's the answer for part B. There we're supposed to find the time that it takes the propeller to turn to a certain angular distance. We knew what the distance was. We knew the angular velocity from part A, but we had to convert from degrees to radians. Okay, now we go to part C. In part C, we're supposed to find what is the tangential speed of the tip of the propeller. So if I take the very tip of the propeller and I want to know how fast is this moving, what is the velocity equal to, the tangential velocity, we have to have a conversion factor. And it turns out that the tangential velocity, v, is equal to the omega, the angular velocity, times the radius. Just like the theta, or I should say the distance, the arc length distance. I'm looking at the wrong variable here, but if you think about the actual distance this covers right here, this is called arc length of the circular motion, s, that is equal to the angular distance theta times r. And then if you want to know the tangential acceleration, that is equal to alpha times r. So you can see that the relationship between the linear units along the edge of the circular motion to the rotational units, theta, omega, and alpha, can be made by using these three equations. Simply multiply the rotational variable by r, the radius of the circular motion, and you get the tangential units for distance, velocity, acceleration. All right, so using that relationship, we want to know that the tangential speed, which is v, so therefore we can say that v, the velocity along the tangent of the motion, is equal to omega times the radius r, and omega was equal to 209 radians per second. And remember, radians is a non-unit. It's like it's not there, but just for clarity, I'll write it. I multiply that times the distance from the center of the motion to the edge, which is the length, which is 1.2 meters. And notice that the units will be meters per second because radians is one of those non-units. We don't have to mention that. So we take 209 times 1.2, and that gives us 251 meters per second. So that means the velocity along the tangent of motion at the very tip of the propeller tip, is 251 meters per second. Let me circle the other answers here for clarity. There we go. And then finally, for part D, we're supposed to find what linear distance does the tip cover in 1 second. So if the propeller is rotating and we want to know how far the tip of the propeller covered along that rotational motion in 1 second, again, we can say, well, distance equals velocity times time. So what we want here is we want distance equals velocity times time, but velocity can be written as omega times r. So this is equal to omega times r times time. And omega is equal to 209 radians per second. And again, radians is one of those non-units that we don't have to mention. There we go. Then we multiply times the radius, which is 1.2 meters. And notice that is the part that we did in part C already. That is actually the velocity along the tip of the blade. And then we multiply times the time because velocity at times gives us distance, and the time is 1 second. So that gives us a distance of 251 meters. And so let me circle that as well. There we go. And so that's how we find the tangential velocity and the tangential distance along rotational motion, as well as the in part A, we're supposed to find the angular velocity. In part B, we're supposed to find the time that it takes to go a certain angular distance. So this is actually a really good example to kind of get you familiar with how to deal with rotational motion and the new variables that come along with rotational motion, and how we can convert from rotational variables to linear variables along the edge of the rotational motion. Okay, hope that helps, and now I'll come up with some other examples where you actually will apply the same equations and also the equivalence between rotational motion and linear motion using the equations of kinematics. So that will then come up in the next videos.